Hi, everyone. Welcome to my talk on a practical guide to graph databases. Before we get started here, I guess, has anybody here used a graph database before? Which ones did you use, Neo? Anybody else? So this is a new topic for most people. So let me tell you a little bit about myself. My name is Dave Bechberger. I'm an architect and a full stack developer. I've been developing for full stack software for about 20 years now. That's everything from high performance, low latency distributed data platforms through high performance web apps built on top of those to standard line of business and enterprise applications. For the past couple years, my focus has been on building out distributed high performance big data platforms, particularly those built on top of graph databases. That's why I'm here to talk to you, because graph databases are kind of my thing. They're the thing I really enjoy working with, and I like helping other people use them to their fullest potential. So for the past couple of years, I had been working as a consultant, basically through a variety of companies, from financial sector to oil and gas to bioinformatics, helping them use graph databases inside their systems to their fullest potential. Currently, I'm the chief software architect for a company called Gene by Gene. We are a bioinformatics company that specializes in genetic genealogy. And we're using a graph data. We're basically working on breaking up our monolithic SQL Server.NET application. And as part of that, we're using a graph database to help out where it makes the most sense to speed up that process. So as I said, what we're here to talk about today is graph databases. So why? Well, graph databases are a hot thing. They're probably the hottest thing in data stores right now, I know. Data stores are not, the sexiest technology out there, but as we all know, having your data store work well, solid, and fast is great. The best thing you can have with your data store is that nobody knows it exists, that it just works for everybody. So this chart shows basically different types of data stores and their popularity since January of 2013. In that time, the popularity of graph databases has jumped 800%. I've been working with graph databases almost exclusively for 3 years or so, and I can tell you in the past year, they've actually gotten significantly more traction than they had in the previous 2 years that I worked with them. Previous 2 years, there was a lot of companies that were working and using them as like little proof of concepts, little research projects, things like that. Now companies are coming out and they're using them in full-on production mode, especially with the release of Amazon Neptune and Azure's CosmosDB's Gremlin API. It's really provided a kind of legitimacy to them as a first-class data store that people are really seriously considering for projects they're working on. So you can't have a talk about graph databases without talking a little bit about graph theory, because graph databases are based on graph theory. Graph theory is that mathematical construct we probably all learned back in university and forgot quickly thereafter. But basically what it comes down to, it was invented by this guy, Leonhard Euler, in the famous 7 bridges of Königsberg's problem. And basically what it did is it came up with a system allowing you to abstract out, basically it was allowing you to abstract out real-world concepts into abstract nodes and relationships between things, which are called nodes and edges in graph theory. Why does that matter? Well, a graph data store, it's a type of NoSQL data store, and it's based on using those structures to build efficient methods to traverse and represent those relationships. So when you look at it and what I think of as the NoSQL spectrum, you go from the data complexity of being the most simple to the most complex. And the complexity really comes down to how data is related to one another. In the simplest end, you have a key value store. This is your Redis, your React, your DynamoDB, your Aerospike. It's basically where your data has no relation other than to itself. You get a little bit more complex. You want to have some relations between other fields, other properties. You get something like a wide column or a column-oriented data store. This is something like Cassandra, Apache HBase, or Google Cloud Bigtable. Get a little more complex as far as relationships go, you get a document database. A document allows you to have complex relationships inside a document, and even some minor joining across documents. But really, when it comes down to it, each entity is a document itself. Then you get to the relational database. The relational database is what we all know, we've all used for many, many years. We're all very familiar with how they work and the basic constructs around them. This is your SQL servers, your Postgres, your Oracles, your MySQLs, what we all probably use every day in our normal day-to-day work. And then you have graph. Graph allows you to deal with more complex relationships than are effectively and efficiently stored in a relational database. Why is that? What do I mean when I say that? I mean, relations are in the name of a relational database. They should be very good at actually storing them. Well, and the truth that when it comes down to it is, in a relational database, your relations are not first-class citizens. Your relations cannot have properties and metadata to themselves, whereas in a graph database, they are first-class citizens. They're allowed to maintain their own metadata and their own properties as they're on that relationship itself, as opposed to having to do something like a bridge table. So in a standard ordered product sort of order system, in a relational database, you have an order table, you would have a products table, and then you would have what I tend to call like a bridge table that would contain the order details. That would be maybe the quantity, the order date, the number of product, the price paid per product. In a graph database, you're actually able to eliminate that need for that third table and have just a node that represents the order, a node that represents the product, and an edge between them that is that the product was ordered. On that edge, you're able to put that metadata about how that actual, the product, the quantity that was ordered, the date it was ordered, things like that on that edge itself, and use that when you're doing what's called a traversal, which is the graph equivalent of a query, to pull that data back out and filter on it. So why would you use a graph database? Well, you go on Google, you'll find tons of examples of different use cases for graph databases. These are just a couple that I thought I would highlight. The first one here is network analysis. This is your friends of friends problem. We've all been on Facebook, we've all been on LinkedIn, we've all seen the, people you may know or people that know this person sort of thing. That's a network analysis problem. This is also referred to as the 6 degrees of Kevin Bacon problem. Every actor is related to Kevin Bacon within 6 degrees of separation. That's this sort of problem. Graph databases are very good at solving this sort of problem because they're very good at traversing those relationships between things. You'll hear me say that a lot during this talk because it's really kind of, if you keep one key fact out of this, that's probably the most important thing. If your problem is about traversing how things are related, then a graph database may be a good solution to your problem. Another common one is a recommendation engine, because a recommendation engine is all about pattern matching and finding relationships between things. Because a recommendation, what do you want to do when you build a recommendation engine? You want to find a profile of someone who's bought items that are similar to your items, and then find the other things that they've purchased that you haven't purchased, so you can give them a more accurate representation or a more accurate recommendation of what they should get. Fraud detection. Fraud detection is a very common use case for a graph database because fraud detection at its heart is really comparing a set of known transactions to a set of known fraudulent transactions and seeing how much they overlap and how similar they are to one another. One that kind of surprised me when I first got into it was master data management. You wouldn't necessarily think of master data management as a graph problem, but it actually fits in the graph space pretty well. Why is that? Because in master data management problem, when you really get down to it, is all about figuring out that entity A in system A equals company B in system B equals entity C in system C. So it's all about relating those items together. So when you make a change to one, you're able to link them together to find out all those things are talking about the same one item. So now that we know a little bit about graph databases, I wanted to talk a bit about the graph ecosystem. I call it an ecosystem because it's large. The graph ecosystem is very large and it's rapidly growing. This slide up here, last count when I was putting it together, I'm not sure I got all of them, but there was 43 different graph data stores up there. When I originally built this slide a couple of weeks ago, I knew of 32, which I thought was pretty impressive in myself. I threw it out to some of the people I know on Twitter that also work with graph databases. Within a day, I got another 10 that I'd never even heard of on this. So that's what I mean. It's a very large and a very rapidly growing ecosystem. And a lot of these have been around for a long time. A lot of these are brand new. So it's continually evolving, and each one is different from the others in certain distinct ways. So in order to kind of help out with this talk, I decided to put them into some big buckets. These are the buckets that I chose. If you ask 4 different people in the graph space, you'll get 4 different sets of buckets. But the ones I basically chose were the big buckets were it's either a graph framework or it's a graph database. And then inside a graph database, it's either an RDF triple store or a labeled property model graph. We'll go into the details of what those things mean here in a second. The first one to talk about is the difference between a database and a framework. When I'm talking about a graph database, I'm talking about a system where the data is both persisted and processed by that system. This is very similar to what we all think of as kind of a SQL database or other relational database. It's good for real-time querying, and it handles both transactional and analytical type workloads. On the other hand, you have a framework. The biggest difference in my mind between a framework and a database is that a framework does not persist the data. It just processes it using graph algorithms. So the data for a framework is loaded from something like your data lake, your data warehouse, your Hadoop file system is a pretty common one. That allows it to work on enormous sized data sets. Because you're just loading the data from something else and usually running it on a distributed analytics engine, something like a Spark, it's allowed to work on enormous data sets that are too big to fit even on a cluster of servers that you would need for something to run them that same analytical workload in an actual database itself. So because you have to load the data, because it takes time to do that, frameworks are really useful for analytical workloads, not really transactional workloads. When you get down to databases, there's two basic types of databases. There's an RDF triple store and a labeled property graph, or a labeled property model graph. In an RDF triple store, each entity in the graph is a triple. That triple contains a subject, object, predicate. That's what your triple consists of. This comes from the semantic web. It's actually got there's a W3C standard for RDF, the resource description framework. RDF data stores, when I think of them, I think that they're great for inferring relationships between things that you may not know that their relationship existed prior. On the other side, you have labeled property model graphs. Labeled property model graphs work on two different types of entities. They work on nodes and edges. When it works on nodes and edges, you have nodes, edges. They also have properties that can be associated with either nodes or edges, and this concept of a label. A label is associated with a node or an edge to give it a type. So it's kind of like a schema thing, where you're able to assign nodes of specific types with specific properties. They're great for basically, labeled property model graphs are great for efficiently being able to traverse relationships that you already know. You can do inference to a degree with labeled property model graphs, but really when it comes down to it, they're better at rapidly and effectively traversing data that are relationships that you know. So here's an example of the same data model using in an RDF triple store in a labeled property model graph. So if you start here at this node that says Bob on the RDF side, if I want to find out what is it that Bob drives, well, Bob drives a Ford, and a Ford is a car. So I'm able to infer from that relationship that Bob drives a car. On the other hand, on the labeled property graph side, you'll see I have a node that of type person where it has a property that the name is Bob, an edge that's directed towards car, and that car's make is a Ford. So I'm able to so as you can kind of see, they both show the same information in slightly different manners. So now that we know a little bit about the different types of data stores that are out there, how do I get my data out? I mean, that's kind of the next question. Once I know what the different things are, how do I get my data out? Graph query languages is an area where the graph ecosystem starts to get a little complicated. And I say it's complicated because there is no standard graph query language across all of the things like there is for SQL. When you write SQL for one database, there might be slight differences across databases, but in general, it's very easy to move from one to the other with slight modifications to your queries. Graph data stores, that's not true. As you see up here, I had kind of bucketed into 5 different types of graph query languages. The first one being Sparkle. Sparkle is probably the only one up there that I would say is a standard for RDF triple. Well, it's the only one that's up there that I would say is sort of a standard, because it's the standard for RDF triple stores. It's part of that W3C standard, so it's well spec'd out and respected by any of the RDF triple stores that I'm aware of. As I said, it comes from the semantic web, and it's that W3C standard. When you get to labeled property model graphs, it gets a lot murkier as far as how you get your data out. The most common one you'll probably run into, and what Neo4j uses, is a language called Cypher. So Cypher was actually created by Neo4j to query their data store. I think it was about 2.5, 3 years ago. They open sourced the spec into what's called OpenCypher. So it's now an open sourced spec. There's a committee that decides it. It's a very declarative language, so it's very much like SQL. It's probably the easiest of the labeled property model graph ones to use for a new person coming on board. And because of that and the popularity of Neo4j, it's probably the most popular one that you'll find out there in the wild. It's certainly the one you'll find the best documentation on. The next most common one you'll run into is Gremlin. Gremlin is part of the Apache Tinkerpop project, which is a very interesting and complex project because it's a database, a graph query language, and a graph engine all at the same time. It's both an imperative and a declarative language. You'll most often find the imperative syntax used. as the declarative syntax is a little bit complex to get working correctly. It's a very powerful language. It's very composable. You can basically get any information out of it that you need out of your graph, but it's got a steep learning curve. It takes quite a bit of effort to really get very efficient at writing it. It's the one that's implemented by, I believe, the most number of data stores out there. I believe there's more that implement the Tinkerpop's Gremlin than Cypher, but that, like I said, this is a constantly evolving landscape, so that number may be changing. That's what both CosmosDB and AWS Neptune use, is their Tinkerpop enabled. The other one you'll find out there on a few data stores is GraphQL. In my mind, GraphQL is better used as a query language for REST endpoints than really a query language for graph databases, but there are a few graph databases that use it as the native query language to get data out. And the last one is just a big bucket of kind of everything else. There's a lot of data stores out there that implement their own specific, data store specific graph query language. They're almost always based off of some sort of SQL, but they're specific to a single system. There is a movement that's out there very recently called GQL, which stands for Graph Query Language, is to basically an attempt to create a standard for property model graph query languages, much like Sparkle. But when I say it's very new, I mean within the past month, this proposal's come out, so there's really, other than a semi-agreement across companies to make it work, there isn't any there's no implementation of it yet. So what you're seeing here is a very simple graph query written in all 5 different languages, or all 5 different languages up there. This is a simple, I want to find a friend of my friends, or I want to find all the friends of my friends, I should say. So the first one you'll see here is Sparkle. One of the things about Sparkle is because it comes from the semantic web, every entity in Sparkle is a URI. So the very first part here where you see this prefix FOAF, basically that's saying anywhere you see FOAF in your query, prefix this on top of it or before it, so it makes your query significantly easier to read, because I don't want to read HTTP : / every time I'm trying to write out a property name. So basically a prefix is that onto everything, and then it's a simple select where, very, very SQL-like in syntax in order to pull your data back. Right below that, what you'll see is Cypher. As you can see, it's a very declarative language where you're basically saying, I want to match things that match this pattern. You'll notice that anything that has rounded brackets represents a node. Anything that has square brackets represents the label on an edge. So it's saying, find me a person, then go out the friend edge. What the star is there, the star 2 is, it's actually saying go out the friend edge twice. So I'm going to go from a person across the friend edge to another person, and then across a friend edge again to another person, and then return me that person's name. Below that, you'll see Gremlin in its imperative syntax. Gremlin has this concept where all your queries in Gremlin will either start with a g.v or g.e. What that stands for is basically, in my graph, give me all the vertices or give me all the edges. And then it then filters down based on that, based on the next what are called steps. So it's basically saying, find me everything that has a label of person, and then go out the friend edge 2 times. Each item here, or each thing here is called a step in Gremlin terms. Dedupe my values and then return me the name. GraphQL, as you can see, is very JSON in nature. It's basically a JSON specification of the data you want to receive back. And the last one down here is, I believe, OrientDB SQL syntax. So a lot of them look very similar to this, but as I said, these are kind of very data store specific, so they may be different based on which one you're looking at. The last part of the graph ecosystem I kind of wanted to touch on was the different visualization options out there. I mean, now that you know what the basis of your database is, you know how to get the data out of your data store, what do you do with it? How do you see it? Graph data by its very nature is very visual. I mean, with SQL data, you can pretty much see, you could see it in a, rows of data on a screen for all that really matters, because it's tabular in that nature. Graph data is all about relationships between things, so being able to visualize those relationships is really important in order to be able to effectively understand what's going on. There's a couple of desktop tools out there. One's open source called Gephi. The other one out there is a relatively newcomer. It's called Arcade Analytics. They both build best desktop tools, or well, Arcade's actually a web-based tool, but it allows you to basically interactively work with your data to basically play with it and figure out what's going on and dig into it and real interactive sort of thing on a desktop. So it's more for data exploration than kind of an end user system. In the middle, you have one that supports has both a web tool and a desktop tool. Tom Sawyer Software and Linkurious are the two most common ones that I've run into in this space. And then you have ones that are very good for basically doing web visualizations. D3, probably most people here that do web development have probably heard of D3. D3 actually has some really powerful tools for integrating with graph databases. Cambridge Intelligence has a tool called Keylines, which is basically, it's not graph specific, but it's very heavy leaning towards graph visualizations. Sigma.js and YWorks are two other companies out there that also have very deep integrations into visualizing graph data. So what do I mean by visualizing graph data? Well, visualizing graph data is usually thought about the two up on the right of the screen here. I always call these node charts. Basically, you're showing nodes and edges with the relationships in between. One thing I want to make sure that trap you don't necessarily fall into is just because your data is a graph doesn't mean you need to represent it to your end user as a graph. And that's where the one on the left comes in. This is actually a demo that Keylines puts out that's basically hotspots of crimes in, I think, Chicago over time. As you can see, the data underneath it is powered by a graph, but the data as you're seeing it makes more sense to a user as a heat map. So to use or not to use a graph database? That's the question we're all here to answer, probably. So everything is a graph. If you go look on the internet, you'll see this is written up there a lot, this concept that everything is a graph. My colleagues and I have been guilty of kind of promoting this concept that everything is a graph. While it's true, everything in the world is pretty much a graph because everything's things related to other things, which is what a graph makes up. What we really should have done when talking about it from a technical perspective is added, but that doesn't mean you should use a graph to solve it. Graph databases are great in certain scenarios, and they're not great in other scenarios. It's not that you can't do it in a graph database, it's just probably not the optimal tool for many use cases. So how do you know which ones it's good for and which ones it's not? Well, it really comes down to exploring the questions. Doing some deep exploration into the questions you're trying to answer will really help you learn, or help you not only learn how to better solve your problem, but lead you towards the right answer for the data store you want to use to solve that type of problem. So let's say you want to do a search or a selection type problem. Give me everyone that works at a specific company, or find me everyone with the first name like John, or find me all stores within 200 miles of, Oslo, Norway. Well, you should probably just use your relational database, or if you have a search server, something like an Elasticsearch or a Solr, they're far more tuned to answer this sort of question very effectively and efficiently. Let's say you want to have a related data question. You want to find, what's the easiest way for me to be introduced into this executive? Maybe you want to, get introduced to an executive in your LinkedIn, and you looked at your LinkedIn contacts and you want to find out how to get between two people, or how do two people inside a company know each other? How is this company related to that company inside my CRM system? Well, this is where a graph answers your question. I mean, if you listen to what I said, the word you'll hear come up over and over again is relations. Relations are really what graph databases are about. Aggregation queries. I mean, how many of these do we all write in probably a single week? How many companies are in my system? What are the average sales for each day? Or, what the number of transactions processed in a day? I always think of these sorts of questions as these are executive dashboard questions. These are the type of things you want to show up on a dashboard that gets surfaced up to the executive level so they can quickly see how the system is working. This is where your relational database shines. This is what relational databases are optimized to do, is these sorts of queries. Use your relational database where it makes the most sense. Pattern matching. Who has a similar profile to me? Maybe this is your product recommendation. Who has a similar shopping pattern to my shopping pattern? Or does this transaction look like it's fraudulent? Or is this user the same as this user? Well, this one's a little more complicated. This one can really depend. It could be a graph. It could be your search server. If I had to look at these three questions, I'd say the first two probably lean towards a graph to me, and the last one probably leans towards using a search server, something like an Elasticsearch to answer that question. Can you answer all these questions with a graph? Absolutely. Is it necessarily the right solution to your problem? Maybe, maybe not. Clustering, centrality, and influence. Who's the most influential person I know on LinkedIn? What equipment in my network has the largest impact if it breaks? What parts fail at the same time? This is in the center of the wheelhouse where graph databases exceed the abilities of something like a relational database. This is where graph databases really shine, is these sorts of questions, as well as the other ones I talked about, but this one, to me, is far and away the easiest one to answer. Yes, this is a graph that you want to do. Or you want to use, I should say. So you still not sure? So what you see here is some work based on a flowchart that my colleague, Dr. Denise Gosnell, worked on. And it's pretty much, what kind of questions you're answering. Are you answering those executive dashboarding questions? If you're answering those executive dashboarding questions, use your relational database. It's optimized for handling those. They've been around for 40 years. All the tools exist. All the tools work with them. Use those to the best of their ability. Are you dealing with more data exploration questions or more trying to find insight and intelligence in your data? Well, then you may want to look at a graph. So what are you going to do with it then? If you want to use a graph database, you don't know what kind of questions are you going to answer? Are you going to answer questions that are really about analyzing large portions of your data? Are you going to load all of the connections on LinkedIn into your graph and then try to find who is the person that has the most influence across the entire system? Well, if you're going to do that sort of questioning where you're really looking at large sections or the entirety of your graph in order to answer it, that's where a graph framework comes in. Those sorts of questions are optimal ones to use a graph framework to help answer. Or are you trying to do one that I want to find out how Bob's related to Jane or Jane's related to Tom, and I want to show the answers to an end user in, say, a CRM system or something like that? That sort of storing and querying operation is where a graph data store, graph database itself is probably the right tool. If you're trying to do both at the same time, you need to go back to the beginning and better define your questions because you're trying to answer two different types of questions with the same solution. As I said, I've spent a lot of the past couple of years working as a consultant, and the one I see more often than not is this one, which is I sold this to management as a graph problem, so we're using a graph database to solve it. As I said, you can solve any of these problems we've talked about with a graph database. It just may not be your optimal solution. Are you still confused? Well, do you care about the relationships between entities more than the entities themselves? If you were going to model this in your relational database, would this take multiple joins, 5 or 6 joins to get the data out, or would you have to write a recursive CTE to do it? Is the structure of your data continuously evolving? One of the real strengths of graph databases is their flexibility when it comes to data and schema. We'll talk about that here in a few minutes, but it allows for the continuous evolution of your data and your schema much easier than a relational database. And is your domain a natural fit for a graph? Is it one of those ones we talked about or one of the ones you can find online? If you can answer yes to many, probably 2 of these questions, you probably have a good fit for a graph database. So now the next natural question comes down to, can't you just do this in SQL? Well, the answer is yes. I mean, none of the questions I've brought up yet have something that hasn't already been resolved in a SQL at least once or twice by people. So let's take a look at it. Let's take a look at the Northwind data model. I mean, we've all probably seen the Northwind data model so many times we know it by heart at this point. But here's a comparison of what a simplified Northwind data model schema looks like in a relational database and then in a graph database. So let's show what does a simple search or selection look like. Well, a simple search or selection query, pretty straightforward SQL query. It's, give me these values from this table with a symbol inner join between the two. This is the comparable gremlin and cipher to match that to answer that same question. As you can see, there's probably, this is a really straightforward SQL query. Probably don't necessarily need to use the power of a graph database to answer this question. As I said, it can work, it can answer it, probably not necessarily what you want to do in the first step. Give me the top 5 ordered products. This is an aggregation type query, same sort of thing. Pretty straightforward SQL. I'm guessing probably everybody in this room has no problem writing this SQL without even looking up what syntax this is. It's a simple select top with a couple of inner joins and an order by. If you look at the gremlin, in the cipher, yet again, it's pretty straightforward. All you're doing is basically defining what sort of pattern you want to find in the graph, and then returning the values. This is where you start seeing the power of a graph database. I want to find products that I haven't, or purchased by other people that I have yet purchased yet. So what you're starting to run into where these SQL queries start becoming not fun to write, not fun to maintain, and not particularly performant. This is a select inside a select with multiple group and order bys, multiple where clauses, multiple joins. Takes a while to sit down and just understand and read what this is. For anyone trying to figure this out, don't worry, I'll share the slides so you can actually look at them in detail, because the text gets very small in order to fit it on a slide. If you look at the Gremlin or the Cipher query, as you can see, they're much simpler. They're much easier to read. They're much more fluid to be able to read through this information to pull out the data. In fact, on the Gremlin query, it's only the first 4 lines that actually answer the question. The last 3 lines are just pulling out and grouping the data. And on the Cipher query, it's only the first 3 lines it takes to answer the question, and the last 3 lines are for grouping and ordering by. This one is not a Northwind data model query, but this is an example of how you can take a recursive CTE and make it a far easier query in a graph. This is basically, I want to see all my employers, supervisors, and the levels. So the way you do this in SQL is you basically have a temporary table with a recursive CTE that's filling that table as it's looping through an unknown number of times in order to get from you, or to get from an employee to the top of that employee's management chain. I don't know if any of you have ever had to write these or maintain them. They're not fun. They're near impossible to get right. No one knows how they work, and they're magic until they don't work, and then you lose all your hair trying to figure it out. As you can see, the Gremlin on the other side is far easier to read, far easier to maintain, and actually far more performant, because recursive CTEs are extremely not performant. They chew up your database resources, and the current project I'm working on is replacing our family tree, which was written in SQL using recursive CTEs with Gremlin for this specific reason. It scales, but it allows us to scale better. It allows us to take some load off of our SQL server that's serving the rest of our application. So now that you know a bit about the use cases for databases and a bit about what you may and may not want to do with it, where do you start? Well, the logical place to start is choosing your data store. This is where you kind of have to make an initial decision. Are you going to do is your problem a framework problem? Is it an RDF problem? Is it a property model, a labeled property model graph problem? What sort of high availability requirements do you have? What sort of transaction volume do you have? What sort of data size are you dealing with? The answer to those questions will really tell you whether you're able to work with a database that fits on a single server, whether you need one that has a single server with read replicas, or whether you need a fully distributed system. All of those exist for any of those things. If you can get away with doing it on a single server, you're obviously going to have far less headache than if you have to go in the fully distributed method. But the fully distributed method gives you high availability things and other things. And then do you want to do hosted or on-premise? As far as I'm aware, there is hosted versions of many of the data stores I showed up there. Probably at least a quarter to a third of them have a hosted version out somewhere. As I mentioned, AWS has Neptune that actually just went general availability about a week ago or 2 weeks ago. CosmosDB has a Gremlin API on top of it. There's other ones out there there's hosted versions of Neo4j, there's hosted versions of Onyx. Any of the graph frameworks can be used on top of, almost all of the graph frameworks use Apache Spark under the covers. Apache Spark is a hosted product in several places, and you can run it on top of that. So what are some of the concerns you have when thinking about a data store? Data consistency. With relational databases, you get a data consistency that's known as ACID consistency. Stands for atomic, consistent, isolated, and durable. Basically what it means is as soon as your data is written, it's a very pessimistic way to actually do data consistency, but what it guarantees you, as soon as your data is written, that data is consistent across everything and will always be there. It's been durable, it's been durably written to disk, and it's consistent across everything. In NoSQL data stores, a lot of them have made trade-offs of consistent or for higher availability. They've made trade-offs to other parts of ACID compliance. The one you'll see out there a lot is it's called base compliance. I know, I didn't come up with a name, but yes. It stands for base availability, so the system is available almost all of the time. It's got soft state, which means that you're not necessarily write consistent or read consistent, but that you're eventually, and the E stands for eventual consistency, which means that data will eventually become consistent across all the different areas. So knowing whether you need ACID compliance or not, or what parts of ACID compliance you need, really will help aid in your figuring out which data store you want to use. Because if you need full ACID compliance, there are certain graph databases out there that provide that. And if you need it, you've automatically narrowed your search down from 43 to a very small number. Once you kind of have that number, or once you kind of are able to narrow down your choices to a smaller number, really explore those choices. Each of the choices have very different pros and cons to them. If anyone has any specific questions, they can come talk to me afterwards. And I don't have time to go through all of the different pros and cons of all of them here. But really explore your choices, understand what you're choosing and what you're giving up by doing that, by that choice, and then beware the operational overhead. Graph databases, I don't want to say they have more operational overhead than relational databases, but their operational overhead can be non-insignificant, especially if you're dealing with highly distributed ones. It's also something that is not familiar to most organizations. Most organizations have DBAs or people that act as DBAs or people that have done DBA work in the past and know how to make those systems run. Graph databases, nobody has that guy. That everyone has to learn that. Somebody on the team has to be the guy that has to learn all of those things in order to make it work. So make sure you factor that in when you're making your decision. So once you kind of made the choice as to what data store you're going to use, it's time to do a little bit of data modeling. The statement you'll often see about graph database, or modeling for graph databases is it's whiteboard friendly. This is really true. And that's because your data model in your graph, because it so naturally fits into the real world domain, tends to be very close to your conceptual model. I always kind of put a little qualifier on there and say it really needs to be a pragmatic conceptual model. Because in an ideal world, you could basically take your conceptual model and make it your graph data model. In the real world, you have to apply the fact that your graph database stores data in certain ways. It has certain optimizations or certain optimizations or features that it has or doesn't have that you really need to take into account when you're working with your conceptual model, or with your conceptual model when you make that into your graph data model. You also have to take into account how you're going to traverse your data. So one of the things with the graph data is the performance of your query is going to be directly related to the amount of the graph that you actually query at any one time in order to answer your question. If you query 100 nodes and edges in order to answer your query, it's going to take twice as long as if you query 50. So if you're able to make your model, if you're able to know that the queries you're most likely to be hitting are the ones you hit most often, and you're able to optimize your model in some ways for that, it's definitely something you want to look at. If you have nothing, if you're starting from an existing system and you don't really know where to start, the first thing I'd suggest you do is just migrate your relational model. If you migrate your relational model across, it will work. What you want to do then, on either whether you migrate your relational model across or you start with your own conceptual model, is really iterate on your data model. Iterating on your data model is a really common practice in graph data modeling that isn't quite as common in the relational data model. In a lot of big enterprises in a relational model, you kick the data modeling over to another team. That team does their work, sends you back, this is the data model you're going to use, and you go and build your application. In the graph data world, you really have to be it has to be much more interactive because, as I said, knowing how you're traversing your data directly affects your query performance. So being able to iterate on that data model to get the most performant and optimized model for your system is something you really need to make sure you build into your plan. Things to be concerned about in data modeling. The one that almost every new graph data, or new person to graph does that I see consistently is what's known as a symmetric relationship. So in graph data modeling, in most graph data modeling, all the data stores use what's called directed edges. That means that you have an in vertex and an out vertex. So the edge goes from one vertex in your system to another vertex in your system. What you'll see a lot of people, especially new to graph, do is they'll put one edge that goes from vertex A to vertex B and an edge that goes from vertex B to vertex A that both represent the same logical construct. In a graph, just because the edge has a direction doesn't mean you can only traverse it in that direction. So you can traverse an edge both in the in direction and the out direction, so there's no need to duplicate that relationship. So you don't need to use symmetric edge relationships. If there's an edge going between two vertexes in both directions and they mean the same thing, get rid of one of them. The next thing I always think is to look out for what I call hidden or anemic relationships. This will happen especially if you migrate your relational database model directly across. So what is a hidden or anemic relationship? Well, let's go back to that initial construct I talked about where you had an order table, a products table, and an order details table. If you migrated that straight across, you'd have 3 different vertexes, you'd have 2 different types of edges. None of those edges would have any properties about them. They would have no metadata on them. Because you now have a graph model, you can get rid of that one vertex and put those properties onto those edges, which will make that edge, a fully fledged part of your graph. Additionally, adding those properties to the edges can be a way to speed up your query, because if you have to go, as opposed to having to go from a vertex to an edge to a vertex to answer a filtering question, I can go from a vertex to an edge. So I've now just chopped out 50% of my traversals. I can answer that question. I can filter in and out in and out nodes quicker if you're able to put those properties on the edges. One of the other things you'll hear about when you hear about graph data modeling is this concept of a supernode. A supernode is often referred to as the Justin Bieber node. What it is it's a node in a graph that has a disproportionately high number of incident edges to the other graphs around it. I know, that probably made no sense to anybody, just what I said, so let me explain it a little bit. So an incident edge in a graph is an edge that either is coming in or going out of a node. Pretty straightforward. A supernode is when you have one node that contains like 10 or 100 or 1,000 times more edges than the average. And why is that a problem? Well, let me give you an example of it. A really common example I like to use for this is addresses. Let's say you have an address and you have a country associated with that address. If you wanted to be, a purist of graph theory and graph modeling, that country would be its own node. But let's say you're in Norway and maybe you ship to Norway and Sweden. Let's say you've shipped 150 million orders. Well, now you're going to have 150 million edges either going into or going out of Norway or Sweden nodes. Like, there's a lot. That's going to be drastically more than anything else in your graph. And it's going to return a problem if you want to basically filter down data filter or have traversals that go through that node to filter out data. So if you wanted to answer a question of like, what's the country for this address, you'd be okay because you're following a single edge incident, or you're following a single edge in to get one piece of data. But if you want to say find every order that's been placed in this city inside Sweden, you'd start in Sweden edge, then you'd look out 75 million orders, and then you'd have to filter it down after that. As you can see, that's quickly going to become a very non-performant query or non-performant traversal. So in that sort of scenario, a lot of times what you end up doing is you'll denormalize that data onto that edge. As I said, this is kind of where that pragmatic part of your data modeling needs to come in, where you're looking at the way you're going to query your data and adjusting your model accordingly. Schema. Schema is kind of a hot topic in the graph world. If you go out and you read most of the data literature or most of the sales literature on data stores, they'll talk about how they're graph data stores. A lot of them will talk about how they're schemaless and how the schema can constantly evolve. That's true. I'm not necessarily saying that having that ability is bad, but if your data store doesn't enforce a set of schema, my suggestion is to make your applications enforce it. And why is that? Because if I have 7 different applications writing to the same graph, I don't want to go out 7 different edges to find out what product was ordered by somebody because application A called it one thing and application B called it a different thing. Just for the simplicity of the thing, enforce that schema at your application level. And because you're doing that, you can make it general. Because the fact that you have the ability to add properties on top of those edges, you can, most of the time, instead of adding specific edges, you can add more general edge with a property of a type or something like, maybe you have a person with phone numbers. Well, as opposed to having a home phone address, a work phone address, a mobile phone, sorry, not address, a home phone edge, a work phone edge, a mobile phone edge, you can make a single edge that just has phone and it has different types inside of it. It allows you to answer questions like, give me all the phone numbers for somebody, or give me only the mobile phone number for somebody, just as easily and much more performant than trying to do it with 3 or 4 different edges. So what next? Now I've told you a little bit about, what to think about when you choose a data store, what to think about when you kind of do your data modeling. Unfortunately, until you choose your data store, what's next is really dependent. What comes next is really understanding what the data store can do for you, understanding the constraints of that data store, understanding the feature set it offers. Certain ones offer things like unique constraints, others don't. Understanding that stuff is really what you need to work through next. And since there isn't really a general statement, can't go into too much detail. So, kind of give a little bit of a summary. What are the good things about graph databases? I mean, I know I just spent the last probably 30 minutes here telling you why not to use a graph database. But as I said, I like graph databases. I think they're very good at solving problems. Part of that is graphs are really flexible. It's very easy, and generally it's very easy to extend your model, to add additional attributes, to add objects, allowing your data and your data schema to evolve at a rapid pace that isn't easily done inside a relational database. They're really great at searching for relationships between items, but if that's not what you want to search, they're probably not the right solution. They're a natural fit for many domains, and in those domains, you'll find that things, it's much easier and more natural to work through a graph database than it is to necessarily try and force that into a relational database. I always think of the relational database, it's the old idiom that if, all you have is a hammer, everything's a nail. Well, hopefully, that relational database is our hammer. We've all used that hammer. We can put whatever we want. We can use whatever we can put whatever we want into it. Doesn't make it the right tool for the job. Hopefully what you'll get out of this talk is at least a little bit of an understanding of what graph databases are good for, and now you have another tool in your tool belt for when it's the right choice. What are some of the bad things about graph databases? Well, the different options about graph databases scale very differently. It's very specific to the data store. Unfortunately, there's no rule of thumb I can give you where if you have this size thing, you want this specific thing. The team working on it really has to learn a new mindset. It's a different way of thinking, looking at your data. It's a different way of thinking about how you query your data, and it takes teams time to learn that. And it's still a very immature space. As I said, it's constantly evolving. It's very, the tooling is not as mature as what we're all used to for relational databases. I mean, relational databases have been around in their current form, probably 40 or 50 years now. They obviously have optimizations that far exceed what exists in the graph data space. The graph data space has been around maybe 10, 12 years for property model graphs. The tooling out there is nowhere near as robust. It's nowhere near as easy to use. I like to think of graph databases as kind of like teenagers. You can eventually get what you need out of them, but sometimes it seems a lot harder than you actually want it to be, or you think it should be. And then the ugly. So the ugly part is really the lack of documentation. There's lots of really good documentation out there for people that are brand new to graph databases and people that are expert at graph databases. There's really a lack of good documentation for people that know a little bit but not enough. It's an area that's really there's a big hole that I'm hoping to work with people to help fill that hole. The ecosystem's vast, it's splintered, and it's rapidly evolving. Because of the immaturity of the space and because it's not as well-defined set of standards and things like that, it changes all the time. As I said, it's very hard to keep up with some of the paces. And the other part here is, hopefully it's helped a little bit, but it's kind of hard for new users to tell good use cases versus bad use cases. Usually the way you do it is by making the wrong choice. So here's some of my advice from kind of the trenches. Graph data stores may be great to solve your problem, but really make sure you understand what your problem is first. Make sure you expect, when you're planning out an application development plan or application development lifecycle, make sure you build in time for trial and error. There's going to be a lot of trial and error. You may start with one data store and find out it's not really the right choice for you and you need to switch to a second one. You may need to do that to a third one. Make sure you plan in time to do that. Your data model is going to evolve. Plan for it. As I said, it's not, in a lot of enterprise applications, the data models are kind of set by a different team, and then that's just what you build against. That's not really the way it works in a graph database, at least not the way to get an efficient data model. Don't underestimate the time it takes bring your team up to speed. I've been guilty of making this mistake with teams I've worked with, is thinking, oh, this will take them a week, and it takes them 2 months. As I said, there's not a lot of great documentation out there sometimes. The tooling's a lot harder. It's a lot more immature. A lot of it's very specific to a single data store. So if you use Datastore A and you learned how to use that tool and now you figured out that's not the right one, you got to go to a different data store, that has a different set of tools that you need to learn how to use. And graph databases aren't a silver bullet. You'll go out there and you'll see, if you go out on the web, you'll see lots of things where people are claiming that graph databases will solve all your problems and everything's, unicorns and rainbows. Reality is, they're really good for some things. They're not as good for other things. And being able to kind of understand that and be able to say, maybe this isn't a good use for a graph database. Or maybe this part of this problem is good use for a graph database, and this part is I want to use my relational database for. So a really common pattern I've run into is to use some sort of graph database as part of a polyglot persistence mechanism. So that's everything I had for you guys today. Are there any questions? So the question was, is it common to see a part of a report, or reporting or a data warehouse database, data lake, something like that being written in a graph database? Actually, usually I don't see that written to a graph database as much as usually the way I've seen that done is it's written, someone uses a graph framework to do processing on it and then stores the results of that processing out to a relational database, sometimes a graph database, but usually most of the big heavy number crunching is done with a framework because especially when you start talking about very large data warehouses or very large data lakes, it's a lot. It can be a lot of data and it can be, depending on the question you're trying to answer, it can take a lot of time to process through it. Is that it? Anybody else?
Is query time predictable? So if it's a product of the number of nodes that's crossed, is that then predictable if you know how many nodes there are?
So the question was, is query time predictable across the number of nodes? The answer to that question is, in most cases, yes. It is sort of, like anything else, it's a computer. If you have 90 things running on the computer and you don't have enough CPU power, no. But basically, given everything being equal, yeah, you can usually assume that twice as much data is going to take twice as long to process. I know, it's a loaded question. So the question was, is scaling the only thing I use to differentiate when choosing a graph database? Which graph database I choose? It's not the only thing I use, but it's definitely it's definitely one of the biggest concerns. Because if you want something that has high availability, well, that immediately removes certain ones that don't support that sort of thing. If you have something that has transaction extremely high read and write transaction level, certain databases don't support multiple write replicas. The other option is if there's familiarity in the team as far as any familiarity with graph databases. I know like there was one person up here that's used Neo4j4. So if all else being equal, if we have familiarity on the team of someone that actually knows how to use this product, I would probably choose the product that they know over other products. And the other one that comes down to is licensing costs, as always. Things cost money. What's the expertise of the team? Just so you know, on that slideshow, that slide that showed all the graph databases, that is a combination of both commercial and open source. Some of those are open source, some of those are commercial. Some of those have open sourced versions of a commercial product. So it's kind of there's a variety of different options out there that you can use to help make that decision as well. Anybody else? Okay, then. Thank you very much. If anybody has any questions or wants any more specific details, feel free to come on down and talk to me.